Good morning, everyone. Am I audible?
Yes, sir.
Yes, sir. Good morning.
Okay. All right. So let's start the recording first, and then if you have any questions about the previous lecture or anything about lab exam, we can discuss that first, and then I'll continue with the lecture. Any questions from anyone? Okay. So if there are no questions, all right. So in the previous lecture, we started looking at the pipes, and we understood how the basic operation of the pipe is. We also took a look at one example for communicating, or actually we use the pipe understanding for reading and writing, right? So what next we are going to do is understand how the operating system is actually implementing the read and the write operation for the pipe, right? So we have seen the read and write operation for the normal files, regular files, but then how it is also done in case of pipe, right? So these are some of the variables that will be used. Now, obviously, these variables are not exactly the same that operating system might have used it internally. I mean, you can take a look at the code for the operating system, the kernel code, and you will know how it is done. But generally speaking, these are the variables that you would need. So, for example, these two are the sort of like hash defines, right? The constants which we would use for the indexing the file descriptor. This is going to be the offset where the reading needs to happen in the pipe, right? So you have a wraparound buffer. When you talk about wraparound buffer, it means that you start at the first byte and then you go all the way up to the last, and then in the meantime, while the writer process is writing, the reader process also might be reading from the beginning end, right? So there are some empty bytes in the beginning. So again, you wrap around, meaning you go from the last byte again, start from the first byte, in the circular manner, right? So basically, it will be like a circular buffer, wraparound buffer or circular buffer. So this offset indicates that which is the next byte that the reading and writing needs to happen. Okay, this is the total size of the buffer. So currently we have just considered it as 64K. But as I said, generally operating system implements it like a 5K. So you can use this as a 5 multiplied by 1024. This is the actual buffer, right? Which is the, as I said, wraparound or circular buffer that we use. And this variable is an integer value which indicates how much data is currently there in the pipe. Okay, how much data is there currently in the pipe. So that is what this information is. These are all the variables that we would need. So now let us look at how the read operation happens. Okay, so in case of read, basically what will happen is that we have to adhere to these conditions that we talked about, right? So the first condition says that if the write end is closed, then the read call will return 0 value. That indicates the end of the input, right? And that is what we will be checking first. So we'll be checking if the write end of the file descriptor is closed, then you just return 0 value, right? This is the first condition that is implemented. Then the second condition is that if the if the reader is trying to read from the empty pipe, then the write end is still open, then the reader process will go into the sleep mode because the data has to be written into the pipe buffer, right? So written into the pipe. Until that point of time, reader will not be able to read anything. So that is the second condition that we have implemented here, which says that if the pipe field is 0, this is the count of the number of bytes that are there in the pipe, right? So if this count is 0, then the reader process will be sleeping. Okay, so you can use this sleeping mode in multiple ways. You can either put it in the sleep for a particular seconds, or you can put it in the pause mode or something like that, which we will look at it somewhat in the signal area. But there are various ways you can put the reader process into sleep mode, right? But this is going to be a blocking read, meaning that the process will not wake up until the data is available in the pipe. Okay, then you check if there is a data in the pipe, then you are going to check. See, the 3 parameters that we pass here is the file descriptor, the application buffer. So this is the buffer where the data needs to be, where the application wants the data to be available here, right? So this the buffer which we are using, which is a pipe buffer, this is an internal operating system buffer. However, this is an application buffer where the data needs to be copied from the file buffer, pipe buffer to the application buffer, and this is the size of the application buffer. So if you remember, whenever you issue a read call, you provide 3 information. One is the file descriptor, second one is the buffer, the variable, the string variable, or the variable where the data has to be read by the application, and then the size of that buffer. Three information we use, right? So the same 3 information is passed over here, and in this particular case, it will be basically we will be checking whether the data in the pipe is less than the size of the buffer, size of the application buffer. If it is less, then you copy all the data from the pipe buffer to the application buffer. But and then you say that how many bytes are returned, meaning that how many bytes are actually read from the buffer. You reset your count to 0 because now you know that you have read all the bytes, and basically the pipe is empty, right? See, pipe is empty, and then this is this read offset is where my wraparounding going on here, right? So this is my wraparound function. So you are saying read offset plus whatever number of bytes you have read, and if this value is greater than the size of the size of the pipe buffer, then you do modulo pipe buffer size, so that it will actually, the offset will wrap around and come at the beginning, right? And then you return how many bytes you have actually read. So this if part is where the pipe buffer has less amount of data than the application buffer size. Okay, that is what is handled here. However, you could have a situation where the amount of data that you have in pipe is more than what application buffer can accommodate. Okay, in that case, you only copy the amount of data that application buffer can accommodate, right? So you copy only these many bytes from pipe buff to the app buff. And then you say how much data you have read, which is same as the size of the application buffer. And then you say that how much data is left in the pipe, right? How much data is left in the pipe, which is pipe field minus the application buffer size. And then you again wrap around the read offset and return how much data that you have read. Okay, so in short, this is kind of the code that you would see in the operating system kernel where the read operation is implemented for the pipe. That is what I wanted to kind of show you. Similarly, for the write operation, again you will have three parameters: the file descriptor, the application buffer, and the size of the buffer. Now, when you look at the write conditions, so the first write condition says is that if the process tries to write where the read end is closed, then the writer process is supposed to be sent a sig pipe signal, and the writer process is supposed to be terminating. Okay. Now, we have not studied signal, but for now, just in the next chapter we'll study that. But for now, just assume that this is what is happening, and that is the condition that is going to be implemented. So we are saying that if for the pipe FD array, if the read end is closed, then the sig pipe signal has to be sent to the writer process. And once the signal is sent to the writer process will terminate. Okay. The second condition is that if the writer writes fewer bytes to the pipe than what pipe can hold, then obviously the writing is guaranteed to be atomic. Otherwise, we will have to basically write whatever amount of space that we have available in the pipe, and then remaining data will have to be written in the next write call, right? So that is what is going to happen. So so that's what we check here. So first we check the amount of data that is there in the pipe. Is it the same as the size of the buffer, the pipe buffer, right? So if it is equal, that means that pipe is already full. Now, if the pipe is already full, we cannot actually write anything, and therefore we are going to be returning 0, right? Meaning that the writer process cannot write anything. So we just return back 0. Okay, as telling that we didn't write anything in the pipe buffer. If there is some space in the pipe buffer, right? So we check that pipe buffer size minus the pipe field. This will tell me how much space is left or how much data is there in the pipe. And if that amount is is greater than equal to application buffer, right? So basically here we are checking that the amount of data which is there in the pipe or amount of empty space which is there in the pipe, is it more than the size of the application buffer? Because this is the amount of data that the writer process wants to write into the pipe, right? So if the number of available bytes, the empty bytes in the pipe, is greater than the application buffer size, then we write everything, right? Then we write everything, and then we update our field variable to say, okay, now we have these many bytes written into the pipe, and then we update our offset, and then we say how many bytes we have actually written. Okay. Otherwise, if the amount of space that you have in the pipe is less than what the writer process wants to write, then we cannot actually write all the bytes into the pipe, right? So then we have to just copy these many bytes, right? These many bytes from the application buffer to the pipe buffer, and then you return the appropriate value. So in short, what I'm trying to say is this is the kind of logic, right? This is the kind of logic which the reader process and the writer process will go through when they are issuing the read and the write call. Okay, that is what I wanted to show you, that this is how you would see that when you go to the kernel code for read and write for pipe, this is the kind of logic that you will see inside. Any questions on that? Okay. So now, we want to use pipes, all right? So what should be the application flow? Like how should the parent and the child process act, or what are the steps that needs to be followed, right, in order to use the pipe. So typically these are some of the events that will, these are some of the steps that we will follow. So obviously you have a main process first, which will be creating the pipe initially before doing the fork. And remember, I told you why that is, right? Because what will happen is that when you do the pipe call, it returns two file descriptors, one for the read end and one for the write end. And you want a parent process to be a reader or writer and the child process to be the other process, right? And both requires those file descriptors. So if you issue the pipe call after the fork, the pipe descriptors will be only available in that one of the processes where you are actually doing the pipe call. But we want the file descriptors to be available in both processes. So we issue the pipe call before the fork. So when the fork happens, those file descriptor arrays are also copied in the data area. Okay. So first we issue the pipe call and then we do the fork, right? So that these the pipe file descriptors will be shared between both the processes. Now, when this happens, basically what will happen is it will basically act like a loop, right? In the sense that you have the file descriptor array, right? So you have a file descriptor array. So let me actually draw something here. One second. Okay, so let's say we start with, so this was my original process, right? So let's assume that this is process ID 10 and this is my original process, and now you have the two file descriptors, right? So let's say this is my FD0 and this is my FD1, right? And then I have so this is my process file descriptor table, right? So this is my process file descriptor table, and this is my system-wide file open table, right? So these are the two tables I have, which I am currently showing, right? So there will be an entry over here also, right? And the two important information that we need here is the offset and the reference count. Okay, I didn't leave the space here, so I'm going to write it here, right? Reference count. Okay, so this is my reference count field and this is my offset field. So what will happen is that when the original process issues the pipe call, this file descriptor will be pointing to, let's say, this entry over here, and this file descriptor will be, let's say, pointing to this entry over here, and then the reference count here will be 1 each, right? Because there is one file descriptor here, one file descriptor here. This is, let's say, the read end file descriptor, and this is the write end file descriptor. Now, so this is what it looks like when I do a pipe call. So when I do a pipe call, this is what it looks like, right? So pipe FD. Okay, now I do a fork. Okay, so when I do a fork, basically what happens is this is my original process and this now becomes my parent process. So I'll call this as a parent process file descriptor, and then the new process file descriptor table will be created, which is going to be for the child process. Right, so child process file descriptor will be created here, and now you also have the same two entries here, because you know that the data area will be copied here, right? So this process, this information will be there in the PCB, right? So this information will be there in the PCB, and so you will also have FD0 and FD1 here as well, right? And both of these are again going to be pointing to the same entries in my system-wide file open table, and therefore this reference count will become 2 each. This is what will happen when you do fork. Okay, so this is what happens, and therefore what will happen is, now let's assume that my parent process is the writer process, and then I close my file descriptor 0 because I don't need the read end. So if I close my file descriptor 0 over here, this will be closed, and therefore now the reference count will go back to 1. But this reference count of 1 is actually referred to it by the child process, because this file descriptor is still open in the child process. Okay. Similarly, I can close the writer end on the child process because I don't need the writing part in the child. I only am going to write in the parent process because my parent is a writer and child is a reader process. And so again, what will happen is that, so this link is gone, right? And then here, this link is gone, right? So therefore, again, here the reference count will be changed to 1, right? So the writer file descriptor from the parent process will be pointing to the respective entry in the file, system-wide file open table. And for the reader side, because the child is the reader for this file descriptor, it will be basically using this entry. So even though the different entries from the process file descriptor tables are pointing to the system-wide file open table, the reference count are for 1 for each of those. And this is how your internal tables will look like when you use the pipe, single pipe. Understood? And that is what it is saying here. The first 3 steps, that is what it means. Okay. Then we have the communication that will be done using the file descriptor read and write system call. And then at the end, we will be closing the remaining file descriptors, right? So once you are done reading and writing using the pipe, and you're done with all the processes, all the process thing, and you don't need the pipe information anymore, so then you will be closing this file descriptor also. So this link will be gone, and so the reference count will become 0, and therefore it will also delete this entry. Okay. Here again, this end will be closed, and therefore this link will be gone, and therefore you close this. This reference count will be 0, and therefore you delete this entry also. So only when the reference count is 0, you delete the entry from the system-wide file open table, saying that that file is really closed. As long as there are more than one, reference counts, then you don't remove the entry from the system-wide file open table. You only remove the entry from the process, process file descriptor table. Okay, because for that process, that file descriptor may be closed, but maybe the other process is still using it. So you can see that when I actually do this fork, it is actually acting like a loop because your reference count is changed to 2. That is what I mean to say. Okay, so now, without further ado, let us look at the actual example, right? To make it very clear to you what all this means and how do we use pipe. Okay, so this is the string that I want to send. Okay, and these are my constants for the index for the read end and the write end for the pipe. Okay, so read end index is 0, write end index is 1. This is my array where the operating system will be populating the file descriptors and some of the intermediate variables that I have. Okay, this is the buffer where I will be reading the data which is sent through the pipe. Okay, first thing that I do is I use a pipe call, right? So you can see that I have a pipe call here, which is done in the main original process, before doing fork. And I told you the reason why we are doing that, right? So this is what we are doing, right? First, so once we do pipe, it will return 2 file descriptors in this array. So the index 0 file descriptor will be for reading, and index 1 file descriptor will be for writing. Okay. Now, what we are saying is that we are considering the child process as the writer process for this pipe. Okay, we are considering child process as the writer process and the parent process as the reader process. Okay, so because of that, we don't need the read read end for the pipe in the child process. So when we close this, this is what I was saying, that it will reduce the reference count to 1 when we close this reader end, right? That is what I was telling you, right? And then similarly, for the writer end, for the parent process, we'll be closing the write end because we don't need that for writing, right? Parent is a reader and child is a write. Okay. Once that happens, right? This is just to display what we are sending to parent, right? And then we are actually using the write system call. So in the write system call, we pass 3 parameters: the file descriptor, the string that we want to send, or the byte string that we want to send, and the size of the data that we are sending. Okay, so this is what the write call is going to look like from the child process. So child is going to, you can see I'm using the file descriptor array with the index of write end, okay, which is 1. So file descriptor index 1 is going to be used in the writer process, and it is going to be sending this byte of this byte stream into the pipe. Okay, now as far as the parent process is concerned, because it is a reader, we are going to issue the read call. Okay, and in the read call, we are going to use the file descriptor read, right? So read end of the file descriptor will be used, and this is the buffer where we want to read the data, and we are saying how many bytes we want to read. Okay, so here you can provide like the large number, because anyway it is going to read whatever is available in the pipe only, right? So if the pipe has less amount of data than what you provide here, obviously it is going to read only that many bytes, right? And then you print whatever you read from the pipe here in the message. Now, because this is the parent, I'm going to wait for the child process to terminate, right? So this is where, once the child is sending the data, it is going to close the write end because it no longer needs the write end, for the pipe, and then that process is going to terminate. So the child process will fall off from, from this bracket, and it's going to terminate. And so the parent process is going to wait till the child process terminates. Once the child process terminates, I'm also going to close the read end from the from the parent side, and then again the parent will also terminate. So this is the flow in which you can use the writer as a child process and reader as a parent process, and child can send the data to the parent process. Now obviously here we have sent the stream of bytes, which is the string, but you could send an integer data, you could send a structured data. It's just that all of that data has to be converted into the byte format, into a stream format. Why? Because the write system call that we are using, or read system call that we are using here, they are not buffered IO calls. They are unbuffered IO calls. And for the unbuffered IO calls, the default data type that it will accept will be stream of bytes, and that's all. Right? So it will not accept anything else but raw byte, right? And that is what we have to provide. So even if you want to send, let's say, an integer data, you will have to convert it using, let's say, I2A. I2A is a function integer to ASCII. You may have used it earlier. So you can use integer to ASCII function to convert your integer data into ASCII code. Similarly, you can use, F2A, floating point to ASCII conversion to convert your float data into the ASCII data, right? So you basically get a stream of bytes, and that is what you need to send it through the pipe. Okay, so that is the only caveat. You can send any kind of data, but it has to be in the raw byte format. Okay, this is what you can you can do to send. So you can see that even though we are not really sharing any any variable, right? So the message is another variable which is used only by parent process, right? And phrase is only variable which is used only by the child process. We are not really sharing that variable, but we are able to send the data from child to the parent. Now obviously here we have hard coded data, but it is possible that maybe child is receiving data from somewhere else, right? maybe it is receiving data from the network, or maybe other processes, or maybe operating system, or whatever it is, right? So you can actually have the dynamic data generated in the child process and can be sent through the pipe. Okay, so that is the reason we are using pipe for communication. Any questions so far? Everything is crystal clear? Okay. So one important thing that I want to point out is that whenever you send a data through pipe, right, there has to be some information that indicates end of message. Why? Because we are sending raw bytes, right? The receiver and the reader process does not know how much data in one particular message is being sent by the writer process. Okay, so there are two techniques, two generally methods are used to do this, right? So one method is that you can have a special message, right, first, that is sent from the writer process to the reader process, which actually indicates how many bytes you are going to be sending, you are going to be sending in the actual message, right? So the first message can be a dummy message that just indicates how many bytes a writer process is going to write into the pipe, which the reader process needs to read. So that is one method that you can use, right? So first you send the length of the message and then you actually send the message. Okay, that is one option. The second option is that you use some special character, as a terminating character for the message. So for example, you can use a null character, or maybe a new line character, or some special character that can indicate that it is an end of message. Okay, so in our example, you will see that I've actually done here +1, right? So if you look at the code, you will see that I've done here +1. So why I have done +1? The reason being that this is going to tell me the size of the data. Right, so I'm saying that this much data I want to write into the pipe, but I want to also send a null character. Okay, I also want to send a null character. So we know that whenever we initialize our string variables, right, the last character in the string array will be my null character. So when I say +1, I will be also sending a null character in the pipe. Okay, so because it's a string data, I'm using null as my terminating character, and that is what even my printf is going to recognize. So when I use a printf here, and when I have a null character, it is going to be printing only the bytes that I have received. Okay, otherwise, if it doesn't have a null character, it will keep on reading the byte, or it will keep on printing the bytes until it really finds a null character somewhere in the memory. Right, so that is what you have to also do. So let me run this code and show you how it works. So again, the output is not going to be very interesting because such programs are actually better understood than sorry, unidirectional out. Right, so you can see that the output is not very interesting. It is just this message is coming from the child process. It is saying that it is sending dummy data return to pipe message to the parent. Right, parent is my reader, child is my writer, and then this message is actually coming from the parent process. It is saying that it has read 27 bytes, right? And what it is reading is basically this message, right? So this information is there in the is basically provided through the code, right? So this is one printf here, and then there is another printf here. Okay, give me 1 second. I think somebody is walking outside. It's making a little noise. All right. So that is how we can communicate from one process to another. Okay. However, if you recall, I did mention that when you use pipe, right? The pipes are unidirectional, right? So pipes are unidirectional, meaning that only one process can use generally a right end and another process can use a read end, because if both process sends the data using the right end, no process knows really that who has written this data, right? Unless again you use some special indicator in the message itself. Let's say maybe you use a process ID or some such thing, right? That indicates that okay, this is the process, this is the data that is written by X process, and this is the data written by Y process, right? But it is very complicated to actually manage bidirectional communication using pipe. So the better option is actually to use two pipes for bidirectional communication, and that is what we generally do. Okay, that way you don't have to worry about much of keeping track of who is sending what data and when and all that, right? So if you really want truly bidirectional communication, right, two-way communication, then the best way is to use two pipes, right? So what you can do is that for one pipe, right, so let's say in this case your FD1, right, the pipe which is using the FD1 array, you can say that in that case the parent is the writer and the child is the reader. Okay, so this pipe is always going to be used by parent as a writer and child as a reader, and here you basically flip the action, right? So here your child is a writer and parent is a reader, which is for FD2. So the code will look very similar. The only difference is that you can use this pipe for sending data from parent to child, and you can use this pipe for sending data from child to parent. That's all. Okay. So again, let us look at an example so that we kind of understand how that is done. So again, we just have two strings here. One where parent is sending data to child, the another where the child is sending data to parent. Right, and then here again we have two arrays, right? We have declared two arrays. We have two pipe calls again, because for FD1 we need two file descriptor, for FD2 also we need two file descriptors, right? And we said that for FD1 parent is the writer process and child is the reader process, whereas for FD2 the parent is the reader process and child is the writer process. Okay, so we basically switch the reader and the writer process, right? Whether parent or child. And so whichever are unused end, right? So for FD1, we know that we are going to be using child process as a reader here, right? So I don't need the right end for the child process, so I'm going to close that. And for FD2, I'm going to close the reader end for the child process because I don't need the read end. Similarly, for the parent, I'm going to do the reverse, right? So parent is the writer for FD1, so I'm going to close the read end, and parent is the reader for FD2, so I'm going to close the write end. Okay, so again, this we are doing so that we can reduce the reference count, and there is no confusion in the code later on. Okay, that is why we are doing this. Now both the process goes into the write mode, obviously, right? And both the process will start writing into the respective pipe. So you can see that the child process is writing into the FD2 file descriptor, and the parent process is writing into FD1, right? So both process can write simultaneously, right? So we know that the child process and parent process are running simultaneously. They are executing simultaneously, right? And we don't have a control over which process will start first and which process will start second, because we don't know when the context switching and all that happens by the operating system. When the processors are allocated to the to which process, we don't know that, right? So we have to assume that both the process will run concurrently or simultaneously, and therefore we have to put the code in such a way that even if it runs simultaneously, there is no deadlock. There is no situation where one process depends on the other and the other depends on the first process, and so nobody is able to get the data. Shouldn't happen like that, right? So once the write calls are done, right, then we can do the read calls for both, right, the child and the parent, and so both will be reading whatever was sent by the other process, and that is what we display. And then we close the used side of the file descriptor, right? So again, it's a same kind of code. The only difference is that we use two pipes for sending data in both direction at the same time. Now, one thing I want to point out is that here you can see that the read call is a blocking call. We know that read call is a blocking call. If the pipe is empty, right, then read will be blocked. So by mistake, if you put the read block before system call before the write in the child process, similarly if you put the read system call before the write in the parent process, both will be going to the read mode first, right? Both will try to read the data from the pipe, but the problem is no one is actually writing to the pipe, which means that the pipes are empty. And this is the situation I was telling you about. This situation is basically a deadlock situation. Why? Because child process is trying to read some data from the pipe with FD1, right, which parent is supposed to be writing. But parent is also in a blocking read where it is expecting data from the pipe with FD2, which the child is supposed to be writing. So the problem is, if you somehow write a code in such a way that the reader goes into the blocking wait and no one is actually writing the data to the pipe, then you can have a deadlock situation, which is not what we expect or should not happen. So one solution to that is implementing threading, and we will again look at it when we look at the threads, POSIX threads, where what you can do is one thread will handle the writing process and the other thread will handle the reading process, or reading from the pipe. One thread will be handling the writing from the pipe. So we can separate the reading and writing activities in the same process using multiple threads. Okay, we will look at this example when we consider thread. But for now, since we are only looking at process management, we don't have a luxury to actually separate it out using threads. Okay, so just keep that in mind. Okay, just keep that in mind. Okay, so that is about using the pipe for sending data in both directions. Now I want to come to this last point for pipe. If you recall, at the beginning of the pipe, I had mentioned that at the beginning of the pipe discussion, I had mentioned that we can actually implement many of the commands that the shell or the kernel has in our own code, right? And that is, again, I want to we have done one such program by implementing PWD command, right? So we had implemented our own PWD command. Now I want to show you that we can also implement pipe in our own code, right? So in short, Unix operating system or Unix based operating system allows us to use the similar functionalities that is implemented in the kernel, that is used in the kernel, to implement our own shell commands, right? So I'm going to use this code connect.c, and I'm going to show you how can we implement pipe in our own code, right? That is what I'm going to show you. Okay, so how do we implement pipe? So when I say pipe, what I mean to say is this. If you recall, what we were able to do is that, let's say I run one process, let's say who. So who is the process which actually displays some data in the standard output. Okay, and then there is another process called WC, which takes the data from standard input. So how do I do that? So if I do redirection of standard input and then I use this, right? Or actually I should do who pipe WC, right? So what is this command do? So who is one process, one application, which is going to run as let's say process ID 10. Okay, and WC is going to be another command which is, let's say, running as a process ID 11. Now the standard output of the who is connected to standard input of WC because we have this pipe operator. So the function of the pipe operator, I mentioned this earlier, is simply to connect the standard output of the first command, right, to the standard input of the next command. That is basically what it does, right? So when I say who generates some output on the standard output device, it's going to be the pipe operator, instead of displaying that value on the standard output device, it will take that content and feed it as a standard input content into next command, which is my WC. And now WC is taking that value as an input. So it is basically using this values, right, this information as an input, and it is doing some it's calculating something, right? So basically it is saying how many lines are there, right? How many words are there and how many characters are there. Now you can do the same thing. You can also do like this, right? So you can use different commands to do the piping together. So ls, or you can do grep, right? So whatever. Let's say grep, and let me search for something, maybe connect. Okay, so I'm saying that whatever ls displays, grep only the connect keywords from there, right? So it is finding that there are two files with connect connect word in the file name, right? So basically I can use pipe for such things. How do I implement this kind of information in our own code? That is what we are going to do. So the important thing to observe here is that we have to get the standard output, and then standard output should be connected to the right end of the pipe. This is what that operation is supposed to happen. So you take the standard output from here and connect to the right end of the pipe. And then for WC program, you take the standard input and connect that to the read end of the pipe. This is exactly what we need to do. That is how the pipe operator for the shell works, for the for the shell works, right? So that is exactly what we are going to do. So what we will do, we will have a pipe, we do a for, and in this case we are considering that the parent is the writer process. Okay, so when we say parent is a writer process, which means that the first command, right, who, ls, these commands that we execute are running in the writer process, in the parent process. Then we use this loop2, which is an excellent command in this case, right? So what we are saying is we will use loop2 and say that whatever is the right end of my pipe, whatever is the right end of the pipe is going to be used as the standard output. So we know that this one is the file descriptor for standard output, right? So one is the file descriptor for standard output. So what we are saying is that my pipe's right end will basically become the standard output. So whenever a program that runs as a parent process, whatever application that runs as a parent process, whenever that process writes something or displays something in the standard output, that data should be treated as if it is going to be the pipe's right end. So we are connecting the standard output to the pipe's right end like this using loop2 command. Okay, same thing we are doing in the child process, but for the standard input. So in the child process, we are saying that loop2 connect my standard input as the, or use my standard input as the read end from the pipe. So what will happen for this file descriptor and for this file descriptor, my reference count will be 2 each, right? Because one will be for this FD write, and then second reference count will be for 1, right? So in that case, basically what will happen? What will happen is, let me draw a new one. So let's assume that this is my, my parent process file descriptor table, right? So what will happen is that, let's say you have FD0 and FD1, right? And then you will have entry for standard output here, right? And then you have system-wide file open table, and then you have an entry for that, right? So let's say this is the entry which is pointing here, and there is another entry which is pointing here. Now, obviously, we have, sorry. Right now, obviously, we have closed this end, so the reference count here will be 0 for this process. But anyway, don't worry about that one. We are worrying about here, this one, right? So here we have this one right now, and let's say somewhere in the system file descriptor here, this one is pointing here, and this is for standard output, right? So this is for standard output. But now what we are doing is, we are saying that instead of using this standard output file descriptor, we are going to be mapping this, right? So we are going to be actually changing this. So instead of going here, we are actually changing this to go to this place. Okay, so originally the reference count was 1 for this part. Now the reference count will become 2. Okay, for this one also. So my file descriptor 1, which is the standard output, is also pointing to the same file descriptor, which is basically my writer end of the pipe. Now, if I close this, my reference count will go back to 1 again, but that reference count 1 is for this file descriptor 1. So my standard output device is still pointing to the right end of my pipe, is what I'm trying to say. So whenever this process writes something on the standard output, it is still being fed into the pipe, not into the standard output device, is what I'm trying to say. Okay, and that is what this loop 2 is doing. That is what the loop 2 is doing. So you can see that I'm closing the right end afterwards, right? So here my reference count goes to 2, right, for this file descriptor, and then I close this one. So my reference count goes to 1, where that reference count 1 is basically my standard output, pointing to that file descriptor, the same file descriptor entry in the system-wide file open table. Same thing happens on the reader side. Okay. Now, if I run a process, right? So now I'm doing exec. So when I do exec, I'm going to run a particular application. I'm going to run a program here, right? Now this program could be ls, could be who, whatever it is. But whenever that program runs, it will display some data on the standard output. But we know that now that data, instead of going to the standard output, it is actually going to be sent to the pipe, because my standard output is redirected to the pipe's right end. Okay. Similarly, when I run this application over here, let's say WC or grep or whatever it is, right? This application is using the standard input to get some data. So instead of getting the data from the standard input, the application will get the data from the read end of the pipe because of this loop 2. And this is exactly how we connect the standard output to the right end of the pipe and standard input of another process to the read end of the pipe, so that we can actually send the data from one process to the other using the pipe, instead of using the standard output or standard input. Is the explanation clear to you? Okay, let me run the code. So you can see what are the outputs that we are getting here, right? And if I run my, our own application, right? So connect.out. Obviously, we can't use this pipe operator here, because we see, when you implement your own kernel, you can do all of these things. You can check the syntax in the way it is provided like this. But because we have implemented this functionality in the user application, right, we have to use this application executable name, right? So I won't be able to use the pipe exec pipe operator, because the pipe operator is actually implemented by kernel and not in my own application, right? So I will have to use the application name, and then I provide the first program which will run in the parent process, right? Which will run in my parent process, argv1. And my argv2 is the another process which will run in the child, which is going to be my reader. Okay, so let's say wc. And now if I see, if you look at the output, this output is exactly going to be the same output as what you got here. Okay, same thing. I mean, you can run whatever other programs that you want to run. Let's say ls. Then again, you get exactly the same values as it is over here. I won't be able to execute this one. The only reason being that currently, if you look at the code, I'm not accepting command line arguments for these programs, right? So argv1, I'm assuming that it is only a single application without any parameters passed to that, any command line parameters passed to that. Similarly, I'm assuming that there are no parameters passed in the argv2 also. So that's why I won't be able to run that the one with the parameter, because here grep is the application and then the parameter passed is the connect to the grep application, right? Which currently I've not implemented in the code, but you can implement that. I mean, it's not that difficult to do, right? So you can actually do that also. Okay, but what I'm trying to say is that this is the technique, this is the method by which you can actually implement also your own pipe. And in case if you write your own kernel, right, you can even implement this code in such a way that actually you can use exactly this syntax for the code. Because see, assume that, let's say that this prompt was actually displayed by your own application, by your own program, right? And you were writing your own shell terminal, right? In that case, you have a control over everything, right? And if you have control over everything, then you can actually implement exactly this particular syntax also. Any questions? Is it understandable? More complex? Easy? Any feedback? I would appreciate. Is the code understood? Am I audible?
Yes, sir.
Okay. It feels like that I'm talking to a screen. So I just wanted to understand that is this program, is this content understandable? Are you able to grasp anything, or this topic becomes very complex? What do you feel like?
Sir, I think we can understand it, but like maybe it is taking some time. We have to read it for 2-3 times.
Okay, but if you revise the recording, if you go through it multiple times, you are able to grasp the topic, right?
Yes.
Most probably.
Okay, most probably. That is not the answer I was looking for. So either, see, in computers, there is nothing like if, right? There is no probability kind of thing in computers. It's a binary answer, yes or no, 1 or 0. Right? So either you are able to comprehend or you are not able to comprehend. Okay, so any questions in whatever I've covered so far? See, another thing I would say is that I understand that this is not your probably this course is little different than your usual programming course, probably because we are normally dealt with application programs and not so much of internal detailed programming at the operating system level or something. But my take on this one is, and based on my experience, I can tell you that if you are able to understand these concepts or these aspects, I think understanding, generally speaking, any programming language or any programming aspect would not be that difficult. Because if you understand the internals of computers, you actually can implement application programs also in a better way, because then you understand how the different components of the system works, right? So actually, you are a better programmer once you understand such internal details of the computer system. Okay, so that is about pipes. Okay. So if there are no questions on the pipes, let me briefly talk about the next chapter, which is signals. Okay. And I know we have roughly 15 minutes, so I won't be able to cover much. But basically, what I want to do is I just want to give you the introduction to signals, right? Because that is another approach of inter-process communication. Okay. So in the first approach, right, the pipe approach, what we studied is that we are able to send the data, the large amount of data in the form of raw bytes from one process to the other. Okay, it can be unidirectional, it can be bidirectional, anything. Okay, but the communication between the process does not always happen in the form of transmission of data. Okay, so the communication is not always in the form of transmission of data. That is not the only way the communication should happen between the processes. There are many other things that the process needs to communicate, right? One process needs to communicate to the other. Now that process could be an operating system level process. It could be your own application program that you are running on a terminal window, whatever it is, right? But so the communication does not happen only in the form of transmission of data. It also happens in the other forms. What are those other forms? Is basically what we call events, right? So there are certain events that could occur, right? And those events also requires communication to the process. So for example, right, what is a signal, right? So signal is another way of inter-process communication. And what is a signal? Signal means that there is some event, unpredictable, unexpected events that happens. For example, you get a divide by zero error, which we call in the computer system or computer architecture world, we call it as floating point error, right? So let's say divide by zero error. Okay, or let's say there is a power failure. Okay, so now if there is a power failure, what so your question would be, what does that mean? I mean, when you have a power failure, it's a power failure and system has to shut down, right? True. But for example, let's say you have an application which is running like a database. Okay, you have a database application which is running. Okay, and database is supposed to be saving data from the memory to the disk. Now, some of the data obviously is in the disk, but then let's say some data is still there in the memory. Now, when the power failure happens, right before the power failure, the computer system gets an indication that power is going to fail. And that indication is when it comes to the operating system immediately sends a signal to all the applications that are running on the system, indicating that power failure is going to happen and your data in the memory is going to be lost. So do whatever you have to do. Okay, do whatever you have to do. Now, the question would be, how would application be able to do anything? So my answer to that question is, what is the frequency at which in India the power signals are running? What is the frequency? We run at 50 megahertz. 50 hertz. Right? Our signal, our voltage signals runs at 50 hertz. Right? So basically, when you have your I don't know if you have studied digital electronics or DSP or something like that, but basically this means that you have the signals of your voltages, right? And this from here to here, this is your 50 hertz. So when you say 50 hertz, how do you convert hertz into the time? 1 divided by that number. So this is basically equivalent to 0.02 seconds. So the size of this wave is 0.02 seconds. Now we know that when you look at computers, right? My computer could be running at, let's say, 3.2 gigahertz. That means if I do 1 upon this one, this number is very, very small compared to this number, which means that I have a lot of time in my computer to do many activities in 0.02 seconds. So, sorry. So 0.02 seconds in terms of computer systems is a very large amount of time. Okay. And so I will be able to do lots and lots of things, right? I'll be able to do lots and lots of things because my speed of the computer is in gigahertz, whereas the speed of the, my voltage signal is 50 hertz, which is very, very, slow compared to my computer system. So what will happen is that as soon as the operating system sends a message to the, let's say, database application, it has this much amount of time to save the data from the memory to the disk, which is a big amount of time. That is what I'm talking about. Okay. So this is what I'm saying, the power failure. Okay. Let's say you set up an alarm in the system. You can do that also, which I'll talk about in this chapter. So let's say you have set up an alarm and the alarm time is elapsed. Okay. So you get an event, you get a signal that says that, okay, alarm is off, right? If the parent process has kicked off a child process or forked a child process and child process is dying or is terminated, then the parent process gets an information about the child process getting terminated. If a user terminates a process by pressing Ctrl C on the keyboard, also the process gets to know about it, and that is how the process terminates. Okay, so what I'm trying to say, these are some of the events that could happen which are unexpected or unpredictable events, and these are some of the events which will cause the signal to come to the process. So the process basically gets an indication, it gets a signal by operating system that something has happened, and depending on the number of that signal, the process will know what has happened. Okay, so we also call signals as interrupts. Why interrupts? Because it interrupts the regular flow of a program or a process. Okay, so process is running, but then something happens, let's say power failure happens, or the child process dies, or divide by zero happens, and so the process gets to know about it, right? So that is what we call signals. Now, these signals are generally referred to it as software interrupts because it is generally the cause of the software application rather than the hardware, except maybe something like a power failure or something like that. So you have, three ways the signal can occur, right? So one is it did something. What it means, a process did something. So your process is running, right? And let's say you did something in the memory, right? You have a pointers in your application, in your process, and you somehow happen to use the pointers which are beyond the scope of the memory for this process. So that is where you get the segmentation fault. I think that many of you may have seen segmentation fault error when you run your application, your pointer based application in the system. So if you don't use the pointers correctly, you will get segmentation fault error because you are trying to access the memory which is beyond the scope of this process's memory, right? So if you access the memory which is outside the boundary of this process memory, then you get a segmentation fault, or you get a floating point error, which I say divide by zero error. So something happened in the code of the process, right, which caused these kind of events, and that could create a software interrupt. Okay, these kind of events are also called synchronous events, right, or synchronous signals. Why synchronous? Because some application code which when the process was running has caused the signal to happen. So divide by 0 obviously is some instruction that is running in the code, right, in the process. So we know that why that happened. The segmentation fault also is some instruction, some malloc instruction, some pointer arithmetic instruction is running inside the code, which is causing the segmentation fault. So whenever some code in the process is error prone, right, and that is where the signal occurs, then we call those signals as synchronous signals. But then there might be certain signals which are asynchronous signals and process does not have anything to do with it, meaning that process did not actually generated that signal or that error, right? For example, a user, right, user can press Control C anytime, right, anytime during the execution of the process, or power can go power can fail, right, anytime during the process. So process does not have a control over when those kind of signal comes, right, and that's why they are called asynchronous signals. So asynchronous means that process does not have a control over those signals when they come, when they are raised, right? But synchronous is where the process does have something in the code which has caused the signal to occur, right? One process can actually send signal to another process, and we will look at that also, right? So for example, a parent process can send a signal to child process and things like that, right? So we'll look at such scenarios as well, right? So here also, process who gets a signal does not have a control over when the other process will be sending the signal. Now, what are the different signals which are there, right, is available in a couple of header files, and the list of the signals. The list of the signals are in slide number 6, 7, and 8. Okay, so these are the signals which are there in in our operating system, and what we can do is we can go to the file system, Ubuntu file system. We can do locate and then signal.h. So signal.h is the file which is our primary header file. Okay, and it is there are various versions of it, but the default one that is generally used is from user include, right? So we are going to open this file in the editor. So let me just open the editor. And then I'll go to the user directory. User include and signals. So this is the header file where there are a lot of functions that are there. Okay, and these functions are basically the forward declaration of the function. Many of these functions we are going to be using. Okay, the signal numbers are actually is in this header file, which is actually included in signal.h. So signal.h has one more include right here, which says bits /signum.h. So it is actually in a separate separate directory, and when we search for signum.h, it is found here. User include x86 so and so bits signum.h, and that is what I am also going to open, right? So open, and then user include x86 and then bits, and then signum, right? Signum. Okay, so signal numbers are defined here, but then these are not all the signal numbers. More signal numbers are also defined in signum generic.h, right? So again, in the same directory, there is also signum generic.h. If you open this file, you have various signal numbers here, right? So these numbers are mentioned here. These are the constants defined, and these are the signal numbers. And that is this list is basically what I have provided you in these three slides. Okay, 6, 7, and 8. So what are these each signal, and what can we do with it? Why do we use signals like these? Obviously, we will look at it when we come back after the exam, right, and break. So let me stop here since it's already 9:46. My request to you is, review the material, while you are in break. I understand that you guys, everyone wants to obviously enjoy, but if you come back and if you have to start from scratch, it will be, difficult again to grasp the material than what we have seen so far. And all of these materials are sort of like incremental, right? We have to build the knowledge on top of one another. So I request all of you to at least revise it a little bit while you are on break. So when you come back, you don't your memory is not like completely empty. I mean, at least you have some remembrance of what we have covered, right? Also, after the break, we will form the groups for the project, because if you recall, one of the things that we have to work in this course is the project, and I usually do in the second half of the semester, because you obviously need to have some understanding of the topics. Then only you will be able to work on some projects, right? So since we have covered up to the process management and pipes, and now we are going to be covering signals, I think you will have fair amount of understanding on the file IO, the process management, and many other topics. So you can think about some projects, right? So I'll form the groups once you come back, and then you can start thinking about what you want to do for the project. Okay. So for that also, I think it is important that you at least have understanding of the topics that we have covered so far. Okay, so that is all I will cover today. Any questions from anyone?
Hello, sir.
Yes.
Sir, can you tell the paper pattern of the medicine?
Why everyone is asking about the paper pattern? So this is the third time I got this question.
Sir, it will be like a coding problems or maybe MCQs or.
See, like I said, I may ask you to write code, but it could be that you have to understand the code and answer based on the code, right? Because it is an online platform. It is difficult to ask a lot of questions where you have to type a lot, right? So I try to avoid such questions, but of course we cannot avoid completely, right? So you will still have to do maybe some coding, maybe some simple text questions and things like that. But there will be more on the objective type questions.
Okay, sir. Thank you, sir.
Yeah. Go after the knowledge. Don't go after the exam. If you have the knowledge, exam can be easily cracked. This is my simple advice to all the students. Acquire the knowledge. Don't only go after the exam, right? If you have the knowledge, you can crack everything. You can crack interviews. You can crack exams, everything, right? Okay. Any other question from anyone?
Sir,
Sorry?
how to make our own shell? Please.
See, basically, it is a simple program that accepts the command, right? So, I mean, you have used scanf or gets or something, right? Which accepts a string as an input, right?
Right. Right, sir.
right? So you get that string as an input, and then you parse it, meaning that okay, you separate them in the words, and then you check what is the first word. Is it ls, is it get, is it something else? And then you check the, depending on the first command, you will have to check the remaining words, right?
Okay,
Does
right,
it
sir.
have all the information or not, right? So basically it is as simple as that.
Right, sir. I understood that. Thank you.
Any other
Sir,
question? Yeah.
regarding project means this is a request. Can we make groups ourselves?
Yes, sir.
Uh,
Please.
I have a problem with that. The reason being, it is very, very difficult for us to manage. Us meaning that me and TAs. Because, see, if you form the groups yourself, we have problems in, identifying, okay, which student is with which group. And then sometimes you may be changing. And even the forming of the groups will take a lot of time, right? Because see, right now, at least right now, we are in the online mode. So you guys will have to communicate between each other and see that which groups will be formed. So besides that, honestly speaking, I'll tell you, once you go out in the world, will you have a choice of choosing your own colleagues?
But sir,
No, sir.
when we form our own group, then our communication becomes easy. Uh,
I do understand that. I do understand that. So I'm not saying that it becomes, I mean, I understand that it becomes easy for you when, when you choose your own groups. I understand. But what I'm trying to say is that if, once you graduate and once you go in the real world out there, will you have a choice of choosing your own colleagues? You will have to learn how to work with different people, right? Different people may have different caliber, different knowledge, different way of working with other people. So I understand that you are comfortable with certain people and you want to try to work with them. I totally understand that. Everybody would prefer that, but in real world, that is not always how it works.
Sir,
So
what
you
will be the
learn
group
how
size?
to work with the other people who you don't know also, right? Managing, forming group by yourself, managing is becoming very difficult. I've tried that earlier, but it becomes very difficult. So that's why I usually go by student ID. I usually go by student ID. So the group of student IDs will be clubbed together. That is how I have done usually in the
sir,
past.
what will be size of each group?
Uh, I've not thought about it, but I'm thinking possibly 4 or so, 3 or 4 or so.
So, sir,
So not
what
a
we
very
can
large
do?
group, but at least sufficient large enough so that you can at least communicate.
Sir, in second semester also we have same condition in discrete mathematics. That
Ah,
Professor Manish Gupta had told to form 4 groups by our own. So means actually he 4 groups by our own. So what you can do, you can make a Google form or like Google Excel sheet so that we can
ah,
write make our own group easily. Because in
okay.
online mode it becomes very difficult if we are
Yes,
not
sir.
not able to communicate with each
Okay.
other.
So let's do one thing. I had tried this once; it didn't work. But since you are, since you are saying that you have already done this in
Yes,
one of the course earlier,
yes, sir.
and it had worked out, I'll give one more try. But I don't want to really hear complaint from anyone saying that I don't have any partner, so I didn't do anything and all that, right? Because then it becomes a difficult for me, because I mean, since you are forming the groups, right, you will have to make sure that you get partners, right? I won't be able to then help you forming the groups, because otherwise I'll have to just put all the remaining students together, those who cannot find the groups. So I don't know if CR is there now or not, but whoever is CR, or whoever is the lead for the batch, you can communicate to the students that maybe during this break time, maybe you can start forming the groups, so that when you come back, we already have the list, and I'll upload the Google Sheet online.
Okay, thank you, sir.
Okay, thank you, sir.
Okay, all right. Thanks everyone.